During this session, we'll take a look at the maintenance and safety considerations of luminaire supports, which are, of course, light posts. Highway lighting is a very important element in traffic safety in that it allows motorists to see the area in the vicinity of the light. But the light support itself can be a potential hazard because it is usually located in the clear zone. In this session, we'll define the purpose and function of luminaire supports, identify the types and elements of luminaire supports, and identify proper maintenance procedures. As we said a moment ago, roadway lighting extends the driver's view of the roadway and roadside. There are two basic types of roadway lighting. This is roadside lighting, which illuminates the road from luminaires located along the roadside or along a median. The second type is the so-called high-mast lighting system with poles that are 75 to 150 feet high. This system lights up relatively large areas, such as freeway interchanges. They are usually located far away from the roadway, thus they are relatively safe. The basic parts of a luminaire system are the tube or bulb and its housing, the mast arm that positions the light out over the roadway, the pole to support the mast arm, the base for the pole if one is used, and the foundation. The mast arm will vary in length from 3 to 30 feet depending on the requirements for each location. It's very important to remember that mast arms of varying length are not directly interchangeable. The pole is usually made of steel, aluminum, or wood. Pre-stressed concrete poles are sometimes used in urban areas where speeds are low. Both wood and concrete poles should not be used in exposed locations where speeds exceed 35 miles per hour because they don't break away. They may fracture, but the damage will be too severe. We believe there are about 6 types of bases used: the shoe mount, the direct embedment, cast aluminum, slip base, frangible couplings. By the way, that's a fancy way of saying that these are special couplings that are meant to fracture or break under impact. And the last type is the shear base. We'll look at each type now. The shoe mount is used to bolt the pole directly to the foundation. The pole is fitted with a shoe that contains the bolt hole pattern. This type of support will not yield when struck. It is a rigid base attachment assembly. Therefore, it should not be used where speeds exceed 35 miles per hour. The directly embedded or butt type mounting is shown here. This is a non-yielding mounting system and should only be used behind curbs. The pole is placed directly in the ground with no base attachment mechanism. The cast aluminum base is an adaptation of the transformer base that was used prior to the 1960s. The fracture characteristics of cast aluminum made it an acceptable breakaway device for larger vehicles. However, the subcompact vehicles that are popular now would not safely break the base because the fracture resistance is too high. Industry has since developed suitable base designs even for smaller vehicles. Here we see the modified aluminum base that has been certified for current breakaway standards. An important maintenance point is that all doors must be kept tightly closed to prevent water, dirt, and rodent damage to the conduit. The triangular slip base design for luminaire poles was an outgrowth of the breakaway sign support research program. The slip base is designed to break away when struck from any direction. This type of base requires the least amount of energy to activate the breakaway action of any luminaire base and therefore is recommended for use on high-speed roadways. It is also recommended on 2-lane roads where the danger of hits from more than one direction is highest. 5 items should be considered when inspecting a slip base. Are the foundation bolts below the slip plate so they will not interfere with the plate slipping action? Is the stub post 4 inches or less in height above the surrounding ground? Is a 16 to 20 gauge keeper plate provided for the bolts? Are the bolts turned to the specified design tightness? If you have a question about the tightness, check with your design engineer. Are washers provided between the plates as well as on top of and on the bottom of each plate? Cast aluminum couplings are commercially available to be installed under the shoe base to make it breakaway. These couplings are strong in tension and weak in shear. That means they break easily. They are screwed onto the base bolts with a threaded top extending through the holes of the shoe base. A nut then anchors the shoe base to the top of the couplings. When hit from the side, the coupling breaks in the groove section, which starts the breakaway action. Field experience indicates that with a weak pole such as aluminum, the pole bends, causing the force to be more pull than ripping. This increases the severity of the impact. A stiff pole is needed to withstand bumper impact and transmit the sideward load down to the couplings. A weak pole will be severely damaged and must be reworked by the manufacturer before reusing. A skirt should be kept around the couplings at all times to keep water and rodents out. Here we see a progressive shear base, which simply means that the rivets or wells will break, leading to a controlled impact. The breakaway action is controlled by the ripping action of each rivet. Orientation of the base is critical. The corner of the base should be oriented toward the expected impact angle for the design action to occur properly. Now let's look at several factors that affect the satisfactory impact performance of luminaire supports. Among these are design factors, placement factors, compatibility of the base and pole, and the environmental situation. These factors enter into design and construction more than maintenance, but you should be aware of several important things to be watchful for to be able to report problems when you see them. Where the terrain is not level, good luminaire performance may be affected on impact. It is critical that the impact occurs at the base, because if the impact is higher, the pole will bend rather than break. Where fill slopes of 6-to-1 or steeper are involved, the vehicle may leave the ground and hit the pole well above the normal impact point. A curb would also cause a ramping action of the vehicle, creating the same problem. This action reduces the probability that the base will perform as desired. The curb action is maximized from 3 feet behind the curb to about 10 feet behind the curb. Thus, every effort should be made to locate luminaire supports on high-speed facilities at least 10 feet behind the curb. It's important to remember that placement between 3 feet and 10 feet is very undesirable. Notice how high the impact point was on this support that was located about 6 feet behind a curb on an urban arterial street. When you see possible problems like these, bring them to the attention of your maintenance engineer. Now let's look at maintenance more closely. We know that maintenance problems associated with any design should have been carefully weighed during the design stage. One way to do this is for you to report to your maintenance engineer for feedback to the designer. Here are some suggestions to reduce maintenance problems. First, the wiring should contain a quick disconnect mechanism at the base of the pole. This prevents the wiring from being broken back in the conduit when the unit is struck. Repairing the wiring is not only easier, but the quick disconnect mechanism also reduces the hazard of live wires arcing. A wire shorted to the pole energizes the whole pole. Debris is another problem area. The debris from a vehicular impact should not end up on the travelway. However, if the luminaire support is installed too close to the roadway, debris from a breakaway base or a slip base can be thrown back onto the roadway and become a hazard. This factor should be considered when selecting the base and the design layout. When this is a problem, be sure and report it back to the maintenance engineer. And naturally, don't forget to remove the debris from the roadway first. One other problem area to be avoided is in installation itself. There are standards for bolt tightness for structural steel supports. Don't follow these standards when tightening the bolts on the slip base. Bolt tightness should never exceed 40% of the full load of the bolt capacity and typically should be about 15%. Over-tightening luminaire slip base bolts is more critical than sign support bolts because the luminaire pole is much heavier and the cantilevered mast arm weight makes it more difficult to break away. Over-tightened bolts only compound the breakaway force necessary to activate the base. Also, don't overlook the washers in between the slip plates either. They're essential to good slip base performance. A 16 to 20 gauge keeper plate must always be provided or the pole may fall down as the bolts vibrate loose. The long, slender pole with the cantilevered heavy luminaire on the mast arm tends to vibrate quite a bit in the wind. Another thing to remember is the ground surface around the pole base must be maintained at no more than 4 inches below the slip plate. Otherwise, a subcompact vehicle could snag on the stub post. Be sure to watch for erosion around these poles. A breakaway design on a side slope can be deadly if the base catches on the soil after separating from the stub pole. The path of the pole base after impact should be checked for interference so that the base will not dig into the slope face as it rotates out and up. It may be necessary to reshape the slope behind the pole in such cases. Many other maintenance problems also exist. A few of these are listed here. Every pole should be grounded. The new breakaway designs may not accomplish this, so the poles are hot. Keep all base openings covered to prevent water, dirt, and rodent damage. By the way, relamping should be done on an area-wide basis to be most economical. Where special conditions cause a film to build up on the glass, they should be washed as often as is required to keep them effective. All poles should be numbered for ready reference. Make sure all replacement or repair parts are compatible with the installation. Fitting in the field is expensive and may even mess up the breakaway system. A safe and functional lighting system can be achieved only through a concerted effort to design good systems and to maintain them after installation. The guidelines provided in this session can assist you in accomplishing your end of the bargain. And now let's look at pavement surfaces. At the end of the session, the viewer should be able to define the purpose and functional requirements of the highway pavement surface, identify the elements of pavements and the characteristics that contribute to improper performance, and identify proper installation and maintenance procedures. Travel lanes may be paved or unpaved. Although there are many miles of unpaved roads in the nation, unpaved highways generally are restricted to lower-level facilities with low speed and limited volume operations. There are very few miles of unpaved major highways. Consequently, this session will address paved surfaces only. By the way, the first rural concrete road was paved in 1909. At that time, a mile cost only $13,535 to build. Things have changed somewhat since this photo was taken, and this roadway has probably been resurfaced and widened at least once. Pavements historically have been divided into two categories, flexible pavements and rigid pavements. Flexible pavements include asphaltic concrete surfaces. Rigid pavements are constructed with Portland cement concrete. Pavements serve the purpose of providing a surface on which to move vehicles. Pavements are supposed to provide a durable travel surface that will withstand repeated wheel loads of vehicles. They're supposed to provide adequate drainage capability. Drainage includes removing water from the travel surface and from the lower portions of the pavement thickness so that the structural strength of the base is not weakened. And pavements are supposed to provide a skid-resistant travel surface that will allow sufficient friction for expected traffic operations. Durability of a pavement is influenced primarily by the quality of materials and the construction techniques used. However, we won't be discussing pavement design here. Friction and vehicle steering factors that influence the safety of vehicle operations are the primary concern of this session. From a maintenance cost standpoint, the major performance criterion of a pavement is that it be able to carry traffic without breaking up, cracking, heaving, or otherwise becoming deteriorated. The selection of materials in the surface course and in the soil beneath it greatly affects the durability of a pavement. It's sufficient to mention here that there are approved pavement designs and they should be used for highway construction. Pavement design itself is the subject of a National Highway Institute-sponsored course that can be obtained for local use. Friction is the capability of a pavement to interact with the tire so that maneuvers such as stopping, accelerating, or turning can be executed without loss of steering control. Friction is affected by pavement drainage, vehicle speed, pavement texture, and the type of aggregate selected. Water on the pavement can greatly reduce friction. Above 40 miles an hour, hydroplaning can occur. When hydroplaning occurs, friction drops essentially to zero. The two most important factors affecting friction are cross-slope and the pavement surface's ability to allow water to move out from under the tire. Surface drainage is essential to avoid hydroplaning. When there's a film of water on the surface, a tire will ride up on the water. Thus, steering control is lost because the tire pavement friction is lost. As we just mentioned, hydroplaning can occur at any speed above 40 miles per hour. Therefore, hydroplaning is not just a rural problem, but also can occur on arterial streets. It's important that surfaces of high-speed facilities provide acceptable friction capability at the expected operational speeds. The design engineer is concerned with specifying the right materials to obtain the desired friction factors for given design speeds. Adequate cross slope is necessary to drain water from the pavement surface. Too great a cross slope creates steering problems. Too little does not adequately drain the surface. Design values of cross slope should be followed closely in construction to balance drainage and steering problems. The cross slope becomes particularly critical when you have 3 or more adjacent lanes. Skid resistance in pavements is a function of the grittiness of the surface texture. A slick pavement offers little skid resistance. A pavement composed of angular aggregate which bites into the tire produces high friction capability. Microtexture and macrotexture are terms that are used to describe texture of the aggregate and of the pavement surface as a whole. The open graded mix was developed to produce a surface that would allow surface water to flow down through a porous thickness and then out to the side on a smooth surface. Although the open graded mix will not substitute for good cross slope, it does perform in a manner that aids friction. Side drainage is not substantially increased. However, water in front of a tire can flow down through the pavement voids away from the tire. This reduces the potential hydroplaning action. This view and the next illustrate the reduction in tire splash between conventional pavements and open graded pavements. Notice the considerable tire splash here on a conventional pavement for a 0.2 inch per hour rainfall intensity. Splashing is hazardous because it often reduces the visibility of other motorists. Here you can see the substantially reduced tire splash from the same truck on an open graded mixed test pavement 200 feet downstream. Look at the pavement wetness differences. The open graded surface appears almost dry in comparison to the smooth surface in the previous shot. Construction methods can affect the performance of the open graded mix. It's important that the impervious layer be smooth so that water cannot become trapped in depression. By the way, impervious means the layer that won't allow water to escape. Here, the level-up course is being inspected before the open graded mix is applied. Flaws in the surface should be repaired immediately. A depression is being fixed here with hot mix material. Milling is used to remove old surfacing material in order to maintain the basic minimum clearances on overhead structures. This operation was so successful that its use has been expanded to many miles of highway. The primary reason is the reusability of materials. By adding a small amount of new asphalt and mixing, the material can be relayed at a substantially reduced cost to the agency. Other factors that adversely affect the performance of the paved travel lane include the surface characteristics that affect steering control. We'll look at each of these 4 factors individually. First, drop-off, then roughness, pavement joints, and uneven lanes. Serious steering problems can be caused by a rutted track alongside the pavement. The tire snags on the pavement edge when the driver attempts to steer back onto the paved surface. Oversteering usually results, and the vehicle can cross over into approaching traffic. This drop-off was caused by applying open graded mix course. The edge should be more gently feathered, but the shoulder surface should not be overlaid with dense mix that would prevent the water from escaping. Drop-offs more than about 1 inch may create steering problems. Ravel pavement edges cause steering problems when a wheel drops off the pavement. Also, drivers tend to shy away from raveled edges, thus reducing the effective lane width. Structural problems will also be created when edges ravel. Rough, bumpy pavement surfaces cause wheel bounce. Friction is greatly reduced because the tire loses contact with the surface. This is particularly hazardous on horizontal curves where the vehicle is being forced toward the outer edge as the vehicle travels around the curve. Transverse pavement cracks that are across the lane produce undesirable wheel bounce, but no particularly unsafe steering problems. Longitudinal cracks, those that go along the center lane, do cause steering problems because the wheel follows the crack. Separated and different pavement elevations can cause steering problems as the wheels are turned across the crack. This crack shown here is not going to be patchable with asphalt. Asphaltic concrete will have to be used to fill the space and provide structural elements in order to repair it. Cracks or joints that have extended through the pavement can cause pumping or washout of the fine material as the wheel passes over the crack. As more and more material is spurted out, the hole under the pavement becomes larger. Eventually, the surface is unsupported and may break out, leaving an unsafe hole in the pavement. These areas should be identified and repaired to prevent more extensive maintenance later on. In the Panhandle in Florida, we've had problems with deterioration and joint separation. Cross-slope between adjacent lanes and the shoulder can cause steering rollover problems when changing lanes. A maximum of 4% change is desirable to reduce this pitch-over effect. This is particularly important on horizontal curves where the shoulder is not super elevated with the main lanes. Wheel ruts in pavement produce uneven lanes and steering problems. Wheel ruts greater than 1/8 to 3/16 inch deep should be identified and programmed for leveling with an overlay. These wheel path depressions are an indication of potential wet weather skidding problems. An uneven pavement surface can trap water and, as we indicated earlier, cause hydroplaning. But wheel ruts are a hazard both in wet and dry conditions. Severe rutting coupled with a vehicle in poor mechanical condition can cause loss of control. In wet weather, water in both ruts can cause hydroplaning. Water in one rut could, because of greater force against the tire on one side, cause the vehicle to spin out of control. Filling in the wheel rut, as shown here, eliminates most of the problem. We say most of the problem because there's still a friction differential between the two pavements. If the friction or roughness of the new asphalt is considerably greater than the roughness of the worn pavement, the greater force on one side of the vehicle could put it into a spin during rainy weather. What to do? When possible, resurface the entire travel lane. If that's not feasible, to place asphalt over the entire travel lane, then eliminate the wheel rut. This way we have eliminated the greater of the two hazards. Roller coaster pavements cause freestanding water where drainage cannot be accommodated. A driver entering water-filled depressions like these could unexpectedly lose steering control. Here's what happens when a driver enters a water-filled depression. Even though this is an urban section, hydroplaning can still occur. Curb sections are prone to cause freestanding water along the edge of the outside lanes, particularly on flat sections of roadway or when the cross slope is steep and inlets are undersized. Inspection of the roadway during or immediately after a heavy rainstorm will identify sections that drain poorly so that corrective action can be programmed. Here we see water standing on I-95. It hasn't had the opportunity to drain off. The median barrier doesn't help the drainage problem, although it does prevent head-on collisions. Problem that has, if you would excuse the expression, resurfaced in the mid-'80s is the high track, low clearance problem. This occurs at railroad crossings and usually happens after the railroad companies have regraded their track. Unfortunately, sometimes they do not adequately resurface the highway approach grade. What happens is the resulting profile can hang up these types of trucks and other types. If a low boy like this, especially when carrying an earth mover or road grader, gets hung up, it's especially dangerous to a passenger train like this. This time it resulted in a derailment near Ocala, resulting in many injuries. We are trying to correct this through better coordination with the railroad companies. But you can help by identifying these problems before an accident occurs so we can regrade the approach. Crossings may not look hazardous, as can be seen here, but look for telltale signs such as gouges in the pavement near the tracks. Many of the factors discussed previously can be identified and corrected during routine maintenance operations. Areas of poor surface conditions, poor drainage characteristics, and hazardous pavement edge condition can be identified during travel to and from other maintenance locations. These items should be visually identified and reported to your supervisor so that improvements can be programmed. Pavement sections near bridges and other structures should be critically inspected. In many cases, pavements near structures settle due to insufficient compaction of fill material behind the abutments. In frost-prone regions, of which we don't have many here in Florida, ice forms first on bridges and steering control can be lost as the vehicle bounces onto the bridge deck. Curves should be inspected to identify pavement edge drop-off ruts from off-tracking vehicles. In severe cases, pavement widening may be warranted where this happens frequently. Sections of pavement containing edge raveling, roadside wheel ruts, and separated pavement joints should be identified and programmed into future maintenance projects. These are indicators of more severe pavement problems, and if left unattended, the repair costs will be much higher. Maintenance field personnel represent a valuable source of information for conditions such as these that warrant future improvement. If a communication mechanism is developed so that comments and suggestions can be transmitted to the proper administrative levels, improvements can be programmed into future maintenance or reconstruction projects. An added advantage of doing this is the courts have ruled in the agency's favor when repairs are programmed, even though they aren't done yet because of prioritization. Knowing what to look for and setting the wheels in motion so that repairs can be made go a long way towards making highways safer places for everyone.